We are lucky to have won this NSF Partnership for Innovation project at Tufts with great collaborators at University of New Hampshire and Face, Pofford, and Thorndike. Also in great collaboration with Geocomp, Dr. Alan Moore for instrumentation. I'd like to give credit to our former students who just graduated and now are working as bridge engineers, John Phelps at Tufts and Paul Lefebvre at UNH, and continuing doctoral student Jesse Sippel, who's here today. A quick presentation outline is that Dr. Bell is going to talk about instrumentation and load testing, and then I'll talk about modeling with various types of models and model calibrations. And then Dr. Bell is going to talk about the practice a little bit and a new bridge design paradigm. In general, the goal of NSF PFI in short is to translate research to practice, and this is the result of our ongoing research that we have. So, Dr. Bell.
Thank you. Our motivation for this is that right about now, and we've kind of seen all these numbers before, is that 1 in 3 of the bridges are near their end of their design life. So we're entering this rebuilding phase. So our innovation isn't so much a sensor or a damage identification process, but it's really a design paradigm. And how do you, we have this heightened public awareness about the problem of our infrastructure. So now it's an opportune time to change that bridge paradigm. And I think that answers a lot of the questions we talked about how do you get owners to want to have an individual sensor or process. It's how do you get them to want to instrument and to care about instrumentation and modeling in general. So the bridge that was selected as part of this project is a small bridge. It is a 3-span continuous bridge over a small river in Barre, Massachusetts. And you may wonder why we would pick a bridge for this kind of big project. And that's because there's a really big landfill right near the bridge. And what works out great for us is it doesn't have a high traffic volume, but it has a very high truck traffic volume. So the bridge gets a lot of excitation, but to shut it down for load test is really not that big of a deal. We're able to do that because it's not in a high traffic area, but again, it has those big trucks coming in. It's a nice smell sometimes. So the Vernon Ave Bridge is a 6 steel girder bridge with a reinforced concrete deck. Everything was cast in place. The beams and decks are composite. It's 3-span continuous, and you can see there's a field splice right about there. So it's about 150 feet long and 75-foot center span. It was ideal for this kind of project because it was no skew and kind of a plain vanilla bridge for us to try this kind of process out to show bridge owners the value that it can have. So our instrumentation plan, because this was research, the bridge is instrumented to its teeth. You can see there's 12 stations along the length of the bridge, and we'll just highlight that north section of Girder 2. So we have multiple stations. Each station either had a set of strain gauges and a tilt meter or an accelerometer, depending on where it was across the length of the bridge. And this is what it looked like across the height. So it allowed us to get all of the information that we needed. What we'll do from this huge amount of instruments is be able then to deselect a subset that would work for different types of bridges. Also, again, because I mentioned it has that landfill and that huge truck, we've put pressure cells at the mouth of the bridge. So we'll be able to correlate that data with, for the pressure cells with the response of the bridge. Also, we're working with Professor Joe Daniels at the University of New Hampshire about pavement management as well, because if any of you have experience in pavement management, a lot of it is done by pressure cells throughout the sublayers in your pavement. So we're trying to look at that for the total health of the bridge. So the instrumentation of this bridge was a little unique because we got in before the bridge was constructed. All of the strain gauges were installed at the steel fabrication yard. That cut costs significantly as well as risk. So in 4 days, 3 graduate students, 2 engineers installed 100 strain gauges. Okay, and they were flat on the surface. So we were able to get a better installation of the gauge, and also you didn't have anybody hanging over water. When we got to the field, the more expensive gauges were installed in the field, like tilt meters and accelerometers. And then we also placed the pressure plates prior to the asphalt pouring and any concrete temperatures in the deck. So there's, again, I told you it was really instrumented. I guess that's the term. Our instrumentation and data acquisition was done by Geocomp here. We have Dr. Alan Marr, who just spoke about similar projects. So you can see the eyesight boxes here. What was done at the fabrication shop was all of the wires were tied at that splice location, and then we were a real partner with the contractor on this, which helped out this project a lot. We were notified when the bridges were coming to the site. Our graduate students were able to go, and then during the shakeout of the girders, everybody knows what the shakeout means, we were able to take those wires. A shakeout is when you take them off the truck. The reason I'm a realist is partially also I'm the daughter of a steel fabricator, so going to the steel fabrication shop is kind of where I live, so that was what I wanted to do. So during the shakeout, we were able to take the wires and put them safely, and also we were able to get on board not only with the steel fabricator, which was High Steel, but also the contractor of the bridge, which was ET&L Corporation, as well as Atlantic Bridge and Engineering, which was the steel erector. So there's all these different people that had to be involved, and if you had their buy-in, all of our instruments went up, and I think 98 out of the 100 are functioning. And they went through transport and direction, so we were pretty pleased with that. So we collected data through our concrete pour, then we did a non-destructive load test. Professor Sanayei will go through a little bit of the research with what we did with that data. And we had 3 well-defined lanes. We had multiple stops. One thing we also used here on the idea of allowing load tests to be not so onerous to bridge owners or bridge users is instead of stopping the truck at predefined locations, which we did just for research purposes, but we also tracked it using an automated motorized total station. So when there's a crawl speed, and we were able to track it in both the X and Y plane, so then we were able to correlate that data with the strain gauges. So it makes the load test go a little bit faster. And with that, I'll bring up Professor Sanayei to talk a little bit about the modeling and the model updating.
One of the speakers talked about the scalability, and it is much easier to do finite element model updating when you do a small example. But when you have a real bridge, then you have thousands of degrees of freedom and thousands of elements. So here we decided to look at two models. One we called enhanced research model that has solid elements for the deck and shell elements for the girders and diaphragms. It has exact geometry, and this has about 50,000 degrees of freedom. Smaller version of that is the enhanced designer model that was made also in SAP using the Bridge Information Modeler BRIM. And this has about 5,000 degrees of freedom. This is not exact, that's roughly, to see if we can get similar results from them, and that would help us when we want to transfer this technology to design companies. So both include exact geometry, system behavior, and also reflect the as-built conditions. So for the enhanced researcher model ERM, we have the detailed finite element model with exact geometry, including pitch and slope and all the non-structural members, structural members, and it has diaphragms, safety curbs, parapets, everything. And the nice thing about this model, it can easily give you access to stresses and strains. Now here we went through several layers of finite element model calibration that we looked at the measured data. This is the solid line below is the measured data. This is the strain gauge at the mid-span, at the bottom of the flange, steel girder flange. And left side is the south abutment, south pier is